It's a great pleasure to introduce Professor Joseph Hoisington from Colby College. And he talk about the energy minimum maps of real and complex projective space. So please.
Okay, so thank you for the introduction. I'd like to thank the people who organized the conference very much for the chance to speak here. Uh, so we'll be talking about the energy of maps between Riemannian manifolds. When we have a map between Riemannian manifolds, the energy is the integral of the norm squared to the differential. So the Riemannian structure on the two manifolds give us a norm on linear transformations from the one tangent space to the other. We take the norm squared of this differential point by point. We integrate it. The usual convention is to multiply by a half. And this is the energy of a map between Riemannian manifolds. Two maybe more familiar special cases of this. When the target of the map, when it's a function to a single real variable, and we view that as a map, this is the Dirichlet integral of a function. And when the domain of the map is one-dimensional, when it's a map from an interval or a loop to a manifold, this is the usual definition of the energy of a path in a Riemannian manifold. Maps which are critical for the energy, maps which are critical points of this energy functional, just like functions that are critical for the Dirichlet integral are called harmonic functions, are called harmonic maps. So two classical familiar examples of harmonic maps are harmonic functions and geodesics. The subject, harmonic maps as a topic, were really introduced by Eales and Sampson in a paper 1964, since then grown to be a very large, very substantial part of a lot of differential geometry and geometric analysis. And past the case where either the target or the domain of the map is one-dimensional, energy starts to interact with the geometry and the topology of manifolds in really interesting ways. What we'll be talking about today, the main theme of this talk, is determining lower bounds for, and if possible, determining the infimum of the energy in a homotopy class of mappings between Riemannian manifolds. So one of our first main results concerns mappings of complex projective space. The setting to begin with, we have complex projective space with its canonical Riemannian metric, its Fubini-Studi metric, say normalized so that the maximum of the curvature is 4. And we'll consider a homotopy class of maps from complex projective space to any Riemannian manifold. We'll call it capital phi. And then we'll consider the induced class of mappings of the two-sphere. So the class of mappings from the two-sphere to the same Riemannian manifold that you get feeding CP1 into a map F from this homotopy class capital phi that we're interested in. We'll call this induced class of mappings the two-sphere lowercase phi. And we'll let A be the infimum of the areas of the image of a map in this class lowercase phi, the infimum of this two-dimensional area in this homotopy class of maps of the two-sphere. And one of our first main results is that it turns out the infimum of the energy in this class of maps capital phi is up to a dimension constant. It's this infimal two-dimensional area. It's proportional to this infimal two-dimensional area. So in a way, this talk will be backwards from what I think is usually a better way to organize a talk. We'll start with one of the main results and fill in some of the background around this, and I'll hope by the end of the talk to have convinced you that this is an interesting result. Questions or comments to begin with? Questions about the definition of energy or what we're claiming here? So let's start with a question. Once we know the infimum of the energy in a homotopy class, the natural question is, when is the infimum realized by a continuous map that belongs to the homotopy class? And as a general remark, a homotopy class doesn't need to, in many cases, does not contain a continuous energy minimizing map. One really really basic and concrete and familiar example of this is the identity map of the sphere of dimension 3 and greater. It turns out does not contain an energy minimizing map. We can spell this out in some more detail that's maybe informative and helpful. So take a stereographic coordinate chart for a sphere of dimension 3 or greater. So a conformal chart to Euclidean space, the complement, say, of the South Pole takes the North Pole to the origin. And if you take a rescaling, a homothety in this conformal chart gives a conformal diffeomorphism of the round sphere. And it turns out you can show that as you take this scaling factor to infinity, and spheres of dimension 3 and greater, the energy of this family of deformations goes to 0. In the sort of usual picture of the round sphere, this mapping looks like conformally pushing the sphere away from the North Pole towards the South Pole. It concentrates a larger and larger neighborhood of the sphere into any arbitrarily small neighborhood of the South Pole that you choose. And it turns out that on the sphere of dimension 3 and greater, this family of maps also has energy decaying to 0. So the infimum of the energy among maps homotopic to the identity of the sphere dimension 3 and greater is 0, but any map homotopic to the identity of the sphere is non-constant, has positive energy. The infimum is not realized in the homotopy class of the identity map of a sphere of dimension 3 or greater. Something to keep in mind, another feature of this example that will be helpful to refer to later, that'll be helpful to keep in mind later, is that with a little closer analysis of what this family of conformal diffeomorphisms of the sphere does, you can show the identity map isn't even a stable critical point of the energy. So the identity map of any Riemannian manifold is a critical point for the energy. It's always a harmonic map. But it turns out on the sphere of dimension 3 and greater, it's not even a stable critical point. It has an index, which turns out is generated by these conformal diffeomorphisms. So the infimum is not always realized within a homotopy class, even in some fairly concrete examples. On the other hand, this is a topic this is a part of harmonic maps that we won't be going into much in the talk today, but one of the really important early results in this area, and something that gives a picture that contrasts with what we've seen with the sphere, combining the work in this very first work by Eels and Sampson with work just a few years later by Hartman, what you can show is that as long as the target of your homotopy class is a closed Riemannian manifold with non-positive sectional curvature, so any homotopy class of maps to a closed Riemannian manifold with non-positive sectional curvature contains a smooth energy minimizing map. Every map is homotopic to a smooth map that minimizes energy in its homotopy class. Just as an aside, my understanding is this is one of the first applications of heat flow methods in geometry. So all of the many other geometric flows, mean curvature flow and Ricci flow, that are modeled on heat flow are also to some extent, I believe, modeled on the flow to decrease the energy of a map that Eels and Sampson and then Hartman developed in this early part of the subject. So there are very concrete examples where the infimum of the energy in a homotopy class between closed Riemannian manifolds is not realized. There are also very general conditions that guarantee that it is realized. A result that's applicable to our discussion for the moment about complex projective space is a theorem of Lishnerowitz that says that holomorphic and anti-holomorphic maps between closed Kähler manifolds always minimize energy in their homotopy class. So sort of a cousin to the fact that complex subvarieties minimize mass, volume in their homology classes, holomorphic maps between closed Kähler manifolds minimize energy in their homotopy class. And what turns out to be the case, what we'll explain in a moment, is that for complex projective space, there's a partial converse to this based on work of Onita. Onita showed that stable harmonic maps of complex projective space, so harmonic maps that are harmonic, first of all, critical points for energy, and then are stable, have a non-negative second variation, have a complex analytic property called pluriharmonicity. And as a result, as we'll talk through in more detail in the next part of the talk, such maps are almost sort of to second order holomorphic maps to Kähler manifolds. Pause for a moment. Questions, comments before we go on. So there are lots of equivalent ways to define what it means for a map to be pluriharmonic, lots of equivalent properties. One of them is that if you precompose with any germ of a complex curve, you take any germ of a map of a Riemann surface into your complex manifold and then feed it into your map, the map of the germ of a Riemann surface is harmonic. If a map of a Kähler manifold has that property, it's pluriharmonic. It's equivalent to a bunch of other conditions. So for complex projective space, what will be important, what's important here, a basic property of complex projective space, but one that's important here and in the argument for the main result at the beginning is the unit tangent bundle of complex projective space fibers not only over complex projective space itself, it fibers over the space of CP1s. It fibers over the sort of Grassmannian of CP1s in CPN. Every unit tangent vector to CPN is tangent to a unique CP1, a unique totally geodesic CP1. And we have this theorem of Lemaire that says that any harmonic map of the two-sphere is a conformal branched immersion. So Onita showed that if a harmonic map of complex projective space is stable, if it has a non-negative second variation, then the map is harmonic viewed as a map of any curve in CPN. In particular, its composition, the precomposition with the inclusion of any CP1 is a harmonic map. So it's a conformal branched immersion along any CP1. So the first part of this we can spell out fairly explicitly. We'll cite in a moment another result of Onita that comes from a Bachner formula, one that we'll just cite. But to see the first part in sort of concrete terms, we have a stable harmonic map. In particular, if we have a map that minimizes energy and it's homotopy class, it's pluriharmonic. So if we feed any CP1 into our map, the resulting map of the two-sphere is a harmonic map. It's a conformal branched immersion. It's conformal along each CP1. So the length of a unit tangent vector fed through the differential of our energy minimizing map of CPN is J invariant, since our unit tangent vector and its rotation by J are tangent to the same CP1 along which our map is conformal. And as a result, the pullback metric, the pullback of the metric by this pluriharmonic, particularly by this potentially energy minimizing map of CPN, is a Hermitian symmetric form on CPN. So far, we don't know that it's positive definite. It might have a nullity, but its nullity will be a complex subspace. The length of a vector fed through it is J invariant. It's a Hermitian symmetric tensor. In fact, Onita showed that for any pluriharmonic map of a closed Kähler manifold that admits a Kähler-Einstein metric with positive Ricci curvature, you have this property that the pullback of the metric is Hermitian, is complex invariant, and that the two form associated to it is closed. Again, in general, it may not have full rank. It may have a nullity, but it's a positive semi-definite Hermitian form. We can form the two form and it'll be closed. And it turns out that you can show for CPN that a pluriharmonic map has to be an immersion on an open dense subset. Again, essentially because of the way the unit tangent bundle fibers over CP1. So if you have a non-zero vector, say a unit vector in the null space of the differential of your map, it's an isolated singular point of the map along CP1, and so the rank increases by 2 in a small neighborhood nearby. You can show that the set on which the differential has full rank is an open dense subset of CPN. So if we have an energy minimizing map of CPN, then supposing only that the target is a Riemannian manifold, it pulls back the metric to a Kähler manifold, some Kähler manifold on CPN, on an open dense subset of CPN, on the open dense subset on which it has full rank. You can also show that wherever the differential of your map has full rank, wherever the differential of your energy minimizing map of CPN has full rank, the second fundamental form of the image is diagonalized by a unitary basis, just like the second fundamental form of a Kähler manifold. So a complex submanifold of a Kähler manifold has a second fundamental form that you can diagonalize by taking equal and opposite vectors, equal and opposite principal vectors that are related by the complex structures. If you take a principal vector with principal curvature kappa and you rotate it by the complex structure, you get another principal vector whose principal curvature is negative kappa. And you can show that this is the case for pluriharmonic maps of complex projective space as well. So in this sense, if we have any stable harmonic, in particular, if we have a map of complex projective space that minimizes energy in its homotopy class to second order on an open dense subset of CPN, it's a holomorphic map to a Kähler manifold. It pulls back the metric to a Kähler metric on CPN, and the image, wherever the differential has full rank, has the second fundamental form of the Kähler submanifold. So let's review some of the points that we fill in so far, and we'll come back to sort of this slide a couple more times throughout the talk as we fill in more of the details, but let's recap what we've seen so far. In any homotopy class of maps from CPN to a Riemannian manifold, the infimum of the energy is determined by the infemal two-dimensional area in the class of maps of the two-sphere that represents its action on pi2, the associated class of maps of the two-sphere. The infemal two-dimensional area in that class is the infemal energy up to this dimension normalization. The infimum is real. So for one thing, holomorphic maps by Lishanarowitz minimize energy in their homotopy class. So there's an important family of instances where the infimum is realized, but it can only be realized by maps that have that property up to second order. It can only be realized by maps that are holomorphic maps to Kähler manifolds almost everywhere into second order. Let's take a pause again. Questions or comments for the moment? So for the next part of the talk, for some of the topics in the next part of the talk, we'll refer to some work of Brian White. We'll refer to this work of Brian White a couple times throughout the talk. And for some background about Brian White's results that may be helpful, they're considerably more general than what we'll mention in the talk here. Just as a personal remark, reading through this paper of his, the way he puts the results is so general that for me, it takes a little while to recognize sometimes that a very special case of this much more general result that he spells out actually has a really sort of, to my mind, a striking interpretation. In general, his work, this work aims to address what homotopy theoretic conditions determine whether or not the infimum of the energy and the infimum of other similar energy functionals in the homotopy class is zero. And one of the things that follows from his result is that in any homotopy class of maps from quaternionic projective space or the Cayley plane or the sphere of dimension 3 or greater to a Riemannian manifold, the infimum of the energy is zero. So we constructed this explicit family of maps homotopic to the identity of the sphere with energy decaying to zero. It turns out that in any homotopy class of maps of a 3 or higher dimensional sphere or a quaternionic projective space or a Cayley plane, the infimum of the energy is zero. So together with the result from the beginning for complex projective space, this determines the infimum of the energy in any homotopy class of maps from a compact rank 1 symmetric space, except for real projective space. This determines the infimum of the energy in any homotopy class of maps of a simply connected cross to Riemannian manifold. So returning to this overview that we have, for a complex projective space, the infimum is proportional to this infemal area in the class of maps of the two-sphere. It can only be realized by maps that have this strong resemblance to holomorphic maps that to second order almost everywhere on an open dense subset are holomorphic maps. But nonetheless, it is realized in some non-trivial cases in a class of maps that are very important in other parts of mathematics and algebraic geometry and complex analysis. And this is different from the situation for the other simply connected compact rank 1 symmetric spaces where the infimum is always zero, and so it's never realized in a non-trivial homotopy class. So this leaves us then with the question, what can we say about real projective space? So what, if anything, can we say about the infimum of the energy in a homotopy class of maps of real projective space? So a first result that shed some light on this. Croak proved that the identity map of real projective space minimizes energy in its homotopy class. So in particular, again, for spheres and for quaternionic projective spaces in the Cayley plane in the homotopy class of the identity, as in all homotopy classes, the infimum is 0. The identity does not minimize energy in its homotopy class. Croak showed that the identity map of real projective space does minimize energy in its homotopy class. And his result is more general, and the more general statement will be significant later in the talk. So let's unpack what Croak's result says. We have a map from real projective space with its canonical metric to a Riemannian manifold. We consider the infimum of the lengths of curves in the target of our mapping that you get feeding a generator of pi1 and an RP1, a prime closed geodesic and RP. And into our map, consider the infimal length of closed curves in that free homotopy class. And it turns out that the energy of our map is bounded below in terms of the square of this infimal length and the target, this infimal length in this free homotopy class and the target. And equality implies that our map is a homothety onto a totally geodesic submanifold. So it's a Moster rescaling, and its image is a totally geodesic submanifold. So incidentally, the results, so Croak's result for RPN gives this lower bound in terms of the squared length of the image of a generator of pi1, just as the result at the beginning for CPN gives the infimum in terms of the infimal two-dimensional area in a class, in the class representing pi2. That's not a coincidence. Croak showed that the infimum, the value for the infimum in the result at the beginning, he showed that it's a lower bound for the energy of a map. And the new content to the result at the beginning is it's the infimum in all homotopy classes. We'll return to that distinction a little later in the talk, but Croak showed that this gives a lower bound for the energy of a map of RPN. So he developed the argument to show that the identity of RPN minimizes energy in its homotopy class. In fact, the argument gives this more general lower bound, and he observed that you can adopt it a little to give this lower bound for the energy of maps of CPN. So like complex projective space and unlike the other simply connected compact rank 1 symmetric spaces, the identity of RPN minimizes energy in its homotopy class uniquely up to isometries by the characterization of equality in Croak's lower bound. But there are a couple of differences, two differences in particular, between what Croak's result says about RPN and what our result at the beginning says and what Leshnerowicz's result says about CPN that we'll talk through now. Again, let's take a pause for a moment before we go on. Questions or comments for the moment? So the first difference, a first difference between the situation for RPN on the one hand and CPN on the other, the group of biholomorphic transformations of CPN, it's non-compact. It consists of all of the projective linear transformations. So all of the linear transformations of the affine space C to the n plus 1 projectivized give biholomorphic transformations of CPN, for example, Mobius transformations of the two-sphere. And Leshnerowicz's theorem says any holomorphic map minimizes energy in its homotopy class. In particular, all of the maps of CPN in this non-compact family minimize energy in the homotopy class of the identity. We have a non-compact family of energy minimizers in the homotopy class of the identity of CPN. Modding out by the isometries if you want, it's the non-compact quotient. It's the quotient of the biholomorphic transformations by the isometries. Croak showed that only isometries minimize energy in the homotopy class of RPN. So the situation for CPN is in some ways more flexible than for RPN. And what will be significant later, in addition, is that if you have a pluriharmonic map from CPN to a Riemannian manifold, a map that has this property that you precompose with a curve and it's harmonic on the curve, and you precompose this pluriharmonic map with one of these biholomorphic transformations of CPN, the composed map is still pluriharmonic and it has the same energy. So the situation for RPN is more rigid than the situation for CPN in this way. Returning, so reminders of what Crookes lower bound says, that the energy of a map of RPN is bounded below in terms of this length squared. The corresponding lower bound for CPN, which the result at the beginning gives us the infimum, is that the energy is bounded below by this infimal area. Both lower bounds are sharp. So again, the lower bound equality holds in Crookes' result for the identity map of RPN. But unlike for CPN, where this lower bound is in fact the infimum in all homotopy classes, seemingly, usually, the infimum in a homotopy class of maps of RPN is strictly greater than Crookes' lower bound. So what we'll do next is sketch out an example where the infimum can be shown to be larger than Crookes' lower bound, and an example that suggests that that's the typical case, that usually, other than in very special circumstances, the infimum is strictly greater than Crookes' sharp lower bound. So the example occurs in RP2, and it has to do with one of the really basic properties of energy, which is that for mappings of surfaces, for mappings for which the domain is two-dimensional, the energy is bounded below, the energy of a map is bounded below by the area of its image, point by point. The energy, the integrand for energy, is bounded below by the integrand for the area of the image. Inequality holds only for conformal maps. Equality between the energy and the area integrands holds precisely where the map is conformal. And we have a theorem of Pao-Ming-Pu for Riemannian metrics on RP2. Pu's inequality says that the area of any Riemannian metric on RP2 is bounded below in terms of the length of the shortest non-contractible curve, and that the unique optimal metric is the constant curvature metric, that equality holds in Pu's inequality only for metrics with constant curvature. So the word for this shortest non-contractible curve is a systole. Again, that's the key term in Crookes' lower bound for energy, the length, the minimal length of a curve in the free homotopy class to which a generator of pi1 maps. So consider an arbitrary metric on RP2 on the one hand, and then the canonical metric on the other. And consider the homotopy class of the identity of RP2, but viewed as maps from RP2 with the canonical metric to RP2 with an arbitrary metric. And for a map that belongs to this homotopy class, first, the energy of the maps bounded below by the area of our metric, by the basic area energy inequality for maps of surfaces. The area is bounded below by the systole, by the minimal length of a non-contractible curve, by Pu's inequality. And this systole, this lower bound in Pu's inequality, is the lower bound for energy in Crookes' inequality. So first, reading the whole inequality here all the way from one end to the other, we have Crookes' inequality for the energy. But moreover, unless our metric has constant curvature, unless it's isometric to our canonical metric up to scaling, the middle inequality between area and systole is strict. And we see that the infimum in the homotopy class is strictly greater than Crookes' lower bound. So Crookes' lower bound is sharp, but in this family of examples, the infimum is strictly greater, other than essentially in the homotopy class of the identity of the canonical metric, the round metric. So in this case, we can be more precise. The uniformization theorem implies that all metrics on RP2 are conformal to a constant curvature metric on RP2. It's a unique constant curvature metric. The infimum energy is actually a minimum in this case. There's a conformal map from the round metric to any metric on RP2. And the area, by the equality condition and the area energy inequality, the area is the minimum energy. So we know exactly what happens for RP2. But you can start with this result about RP2, and using this observation about RP2 and length and area and energy, together with the rest of the things that go into Crookes' argument, you can sort of leverage this to show that for higher dimensional real projective spaces also, seemingly the infimum is usually greater than the lower bound in Crookes' inequality. Seemingly, other than in a homotopy class that contains sort of a very rigid sequence of mappings, the infimum is strictly greater than Crookes' lower bound. Um, what we'll outline now, though, is that in a homotopy class of mappings of RPN, the infimum seems to be determined partly by some of the same information that goes into our result about CPN at the beginning. So again, just want to pause briefly for a moment. Questions or comments for the moment before we continue? So returning to the results of Brian White that we cited before, the conclusion that we cited was that in any homotopy class of maps of a 3 and higher dimensional sphere or quaternionic projective space or the Cayley plane, the infimum of the energy is 0. What's behind that, the technical result that's behind that is the following. So if we have a pair of closed Riemannian manifolds and then a map from the one to the other, take any triangulation of the domain of our map, take the 2 skeleton of the triangulation, and consider all the maps that don't need to be homotopic on the whole of our manifold N, but just have a homotopic restriction to the 2 skeleton. It turns out that the infimum in the homotopy class of our maps is the same as the infimum in this generally larger class of maps that are homotopic when restricted to the 2 skeleton. And for 3 and higher dimensional spheres and for quaternionic projective space in the Cayley plane, the first and second homotopy groups are 0, so you can contract the 2 skeleton to a point in the domain and then feed it into the map, and you get that the infimum in any homotopy class is 0. It's not to, so you can show that the same thing is true, not just restricting yourself to 2 skeletons of triangulations, but to the 2 skeleton of any CW structure. And as a result, so we consider capital Psi a homotopy class of maps from RPN to a Riemannian manifold. And then we'll consider capital Psi hat. We'll consider all the homotopy classes from RPN to the same manifold that give the same homotopy class on RP2. And it turns out that the infimum in the homotopy class that we started with is the same as the infimum in the union of all of these homotopy classes. Is really as a corollary of Brian White's results. And in particular, the infimum of the energy in a homotopy class of maps of RPN only depends on what the homotopy class does to RP2. You can show along the same lines, you can show using Brian White's results that the infimum of the energy in a homotopy class of maps of CPN only depends on what the homotopy class does to the second homotopy group. It only depends on the action on the second homotopy group, which is it's a completely qualitative statement. It doesn't give any idea about how the infimum is determined. It doesn't suggest that there is a systematic geometric or analytic description, but you can show that the infimum in a homotopy class of maps of CPN is the same as the infimum in the union of all the homotopy classes that have the same action on pi2. It turns out you can clarify that for CPN. You can geometrically clarify that. You can show exactly what it is. It's the infimal area in that class. We can show something similar for RPN. So again, the situation's the same. We have a homotopy class of maps from RPN to a Riemannian manifold. We have the induced class of maps of RP2. And we'll let B be the infimal, again, the infimal 2-dimensional area in this induced class of maps RP2. And it turns out that the infimum of the energy in our class of maps of RPN is bounded both below and above in terms of this infimal area. And the upper bound is 2 times n minus 1 over n times the lower bound. In a sense, the width of the interval in which the infimum is pinched is less than 1. If we take the normalization so that the lower bound for the energy in a homotopy class is 1, the infimum is always bounded between 1 and a number a little less than 2. And the lower bound here is sharp. Equality holds in the homotopy class of the identity, and the geometric conditions for equality in general are the same as in Crook's result. A map that realizes the induced lower bound for energy here for RPN of dimension 3 or greater, n greater than or equal to 3, has to be a homothety onto a totally geodesic submanifold. So sort of complementary to Brian White's results. Brian White's results say the infimum in a homotopy class only depends on what it does on RP2. We know that it only depends on that in an abstract sense without any indication of how it may depend on it. This result shows that it can be bounded both above and below, but doesn't by itself imply that that topological data determines the infimum. Yes? The inclusion is the two skeleton of the standard CW structure. If I understand. Yeah, we're considering RP2 as the two skeleton of the standard CW structure. Yeah. Other questions or comments for the moment before we go on? So again, we have in this two-sided estimate for the infimum and the implied lower bound for energy, we have the same characterization, the same rigid characterization of equality as in Crook's result, a map which realizes this lower bound has to be a homothety to a totally geodesic submanifold. That's the case in the homotopy class of the identity. Again, the situation for CPN is different. Once we have one energy minimizing map, once we have one map in a homotopy class, which minimizes energy and has to be pluriharmonic, we can precompose it with any Mobius transformation, any projective linear transformation of CPN, and get another one. So again, the family of energy minimizing maps of CPN where they exist is non-compact, and the situation for CPN seems to be more flexible than for RPN. So let's see. Sort of an aside, but a remark about the result for RPN that maybe gives some interesting perspective. The two-sided estimate for the infimum in a class of maps of RPN in terms of the infimal two-dimensional area is really a corollary of another estimate. So we have a homotopy class of maps of RPN, and we consider that now the induced homotopy class of maps of RPn-1, where again, we're considering the inclusion of RPn-1 as the n-1 skeleton of the usual CW structure, where we form RPN by attaching an n cell in the usual way. And it turns out that the infimum in our class of maps of RPN is bounded both above and below by the infimum and the associated class of maps of RPn-1. And this time, in our result for the two-sided estimate in terms of two-dimensional area, the ratio between the upper and lower bounds increases towards 2 as the dimension goes to infinity. In this case, the ratio between the upper and the lower bound goes to 1. So for very high dimensional real projective spaces, the infimum of the energy is pinched in an arbitrarily small band in terms of the infimum in the induced class of mappings of a hyperplane. And in this sense, then asymptotically, the infimum of the energy in a class of mappings of RPN is proportional to the infimal energy in an induced class of maps of a hyperplane. So returning to our review, first of all, for quaternionic projective space in the Cayley plane in the sphere starting in dimension 3, the infimum of the energy in any homotopy class is 0. It's never realized in a non-trivial homotopy class. For CPN, the infimum is determined by this infimal two-dimensional area. It's realized by holomorphic maps, but can only be realized by maps which resemble holomorphic maps in this sort of precise way based on the property of pluriharmonicity. But nonetheless, this means that where it is realized, it's realized in a flexible way. We have a large, non-compact family of energy minimizing maps as soon as we have one. For RPN, in principle, in the abstract, the infimum of the energy in a homotopy class is entirely determined by what the homotopy class does to RP2. It can be bounded both above and below in terms of the area in this class of maps of RP2. This gives a sharp lower bound, but the characterization of equality in this lower bound, unlike in the result for CPN, is fairly rigid, and the rigidity of this characterization of equality, to my mind, suggests that the situation for the infimum for RPN is probably more complicated. That the infimum is usually not probably going to be the infimum in this result. It will probably fall somewhere within the range that the estimate gives, but not be not always be equal to the lower bound that we get. Nonetheless, it is realized in some cases, again, in contrast with the simply connected spaces other than CPN, where it's never realized in a non-trivial class, where it's never realized, it's not realized in the homotopy class of the identity. In RPN, the identity map minimizes energy in its homotopy class. And then as a remark, sort of an aside, in all of the simply connected compact rank one symmetric spaces, you can phrase the result by saying that the infimum of the energy in a homotopy class is proportional to the infimum of the energy in the induced class of mappings of a hyperplane. The constant, the proportionality is zero because the infimum is always zero for spheres, quaternionic projective spaces in the Cayley plane. It's in terms of the constant by the area estimate for CPN. Asymptotically, that's true for RPN as well, but it seems not to be true on the nose. So we'll finish up talking a little about some questions and some goals for work related to this that seem, to my mind, like they could be interesting directions for future work. A first question is, do these results for the canonical metric on CPN extend in any way to other Kähler metrics on CPN? And as background to this question, a lot of the results, a lot of the things that go into these results about CPN have natural extensions, not just to the canonical metric, but to any Kähler metric. Just to take one example, if a map of CPN is pluriharmonic viewed as a map of CPN with a canonical metric, it's pluriharmonic viewed as a map of CPN with any Kähler metric. This is a general property of pluriharmonic maps. If it's pluriharmonic with respect to one Kähler metric on the domain, it's pluriharmonic with respect to any Kähler metric. Lots of the other things that go into this result for CPN have natural extensions and generalizations and make sense, and you can talk about them for any Kähler metric on CPN. There are a few key points in the argument where I don't see a way to get them to work without the homogeneity of the canonical metric. The way that the unit tangent bundle of the canonical metric fibers over the space of CP1s in a homogeneous way, but almost everything else about the proof works in a sense, at least gives a result for any Kähler metric. So it seems, to my mind, it seems like this result for CPN as a symmetric space could fit into a more general result that describes arbitrary Kähler manifolds biholomorphic to CPN. An example of a question that I don't think the answer is no to: must a stable harmonic map of any Kähler manifold biholomorphic to CPN be pluriharmonic? Another question was, I didn't put this on the slide because I understand it's a substantial topic that I'm only a little familiar with and have just started to try to learn more about. But what is known, I don't know what is known, I don't know how much is known about the properties of a singular set of a pluriharmonic map of CPN. So we know that it's non-singular, we know that the differential has full rank on an open dense subset. Can we characterize any more precisely the singular set, the set in CPN where the rank, the differential of a pluriharmonic map is not full? For RPN, as a general goal, can we determine the infimum of the energy in a homotopy class of maps of RPN more precisely? And there are many forms that such a result could take. Can we improve on the estimates in the result so far, or can we show that the estimates given by the results so far are optimal, that the infimum can fall anywhere within this range? Can we clarify any more what geometric and what topological data influence the infimum of the energy in a homotopy class of maps of RPN? And maybe taking a step back, we should ask, is there sort of a concise, comprehensible result that describes the infimum of the energy in a homotopy class of maps of RPN? There's a straightforward answer for spheres and quaternionic projective spaces in the Cayley plane and that it's always zero, it turns out that there's a sort of clear, concise geometric description of the infimum for maps of CPN. Is there such a result for RPN? And if so, what geometric and topological data inform it? And a last point would be to study stable harmonic maps of RPN. So the results that we've outlined about the infimum of the energy parallel what's known about stable harmonic maps of these spaces, parallel what's known about the existence of maps that are critical for the energy, and then are stable critical points. So Onita and Jin and Lung, their work of these people together shows that there are no non-constant stable harmonic maps of the sphere and of quaternionic projective space and of the Cayley plane, nor are there any non-constant stable harmonic maps to any of these spaces. So the sort of the global fact that in all homotopy classes of maps of these spaces, the infimum of the energy is zero, parallels the infinitesimal fact that there are no stable critical points, no non-constant stable critical points. To my knowledge, there aren't any results of this type for stable harmonic maps of RPN. Again, there are non-trivial examples. The identity map of RPN is a stable critical point, but the methodology that gives all of the results, the Onita's result earlier that we cited, that the stable harmonic maps of CPN are pluriharmonic, and that none of the other simply connected compact rank one symmetric spaces have any non-constant stable harmonic maps, does not work, breaks down in an important point for real projective space. So what can we say about stable harmonic maps of real projective space? So that was everything I intended to tell you guys, but thank you very much for your attention. I'd be glad to talk about questions if there are any. Here.
Thank you very much. Very nice talk. So if there is a comment or question. So I have a question. So
Yeah.
I think it's related to your last question, but you establish some sharp estimate of the lower bound of the energy, and you mentioned that equality holds when the map is opposite to the total geodesic.
Yeah, a homothety to a totally
Yeah.
geodesic submanifold, starting in dimension 3 for RP3 and greater. It's
Okay.
not true for RP2.
Yeah, so I'm wondering what happened when you consider the homotopy class which does not contain the total geodesic map. So
Yeah, so
can you estimate the infimum of such a kind of homotopy class? If
well, yeah, so that's in such a homotopy class, if the infimum is the lower bound, the d sub n times b here, then there is no energy minimizing map in that homotopy class. But it may be, as far as we know so far, it may be that the infimum is strictly greater than the lower bound and no greater than the upper bound. And that it admits an energy minimizing map, but you wouldn't have the same conclusion. You wouldn't have the same conclusion. It may also be, it may be that the conclusion is true. It may be that there is an energy minimizing map and that map is a homothety to a totally geodesic submanifold, but it wouldn't be because of the proof of this result. Mm-hmm. As far as we know so far, that could be the case. Mm-hmm. And yeah, I would like to know. I would be curious to know if that is the case. Maybe to have an answer to that someday. Yeah.
Okay. Thank you.
Yes. Yeah.
Is there any comment or question? If not, let's thank speak again.
Yes. Thank you guys. Yeah.